Good afternoon, everyone. Welcome to this virtual EOL seminar. We are lucky to have not one, but two speakers today. It is my great pleasure to welcome Dr. Ankur Desai and Dr. Brian Butterworth. Interestingly, Ankur Desai was an NCAR ASP postdoc fellow after getting his PhD at Penn State in the Department of Meteorology. Dr. Desai is now the Reed Bryson Professor of Climate, People, and Environment in the Department of Atmospheric and Oceanic Sciences at the University of Wisconsin-Madison, where he heads the Ecometeorology Lab. This lab specializes in ecosystem atmosphere observations of carbon, energy, and water using Eddy covariance flux towers. Dr. Butterworth is an Ecometeorology Lab member at the University of Wisconsin-Madison as a postdoc research associate. Interestingly, he was a Colorado local, where he did his master's in geography at the University of Colorado before getting his PhD in atmospheric science at the University of Albany. This past summer, they and colleagues published an overview paper in BAMS on the NSF-funded CHEESEHEAD project. Both EOLs, ISFS and ISS, supported CHEESEHEAD, which is the topic of Ankur and Brian's presentation today. We are using Slido to pose questions, which you can ask at any time during the seminar. Do not be alarmed if you do not see your question on the Slido window, because we are archiving all questions that will be revealed during the Q&A portion of the talk at the end of this presentation. Dr. Butterworth, Dr. Desai, we welcome you to EOL, and the virtual stage is yours.
Thank you very much, and thanks for having both of us. And I'm sorry we can't be there in person in our old stomping grounds, but I'm really excited that we still have this opportunity to get you to some initial and exciting results that we're seeing from our 2019 experiment in northern Wisconsin. So, as you know, CHEESEHEAD, which is a picture of one here stolen from the internet, it stands for Chequamegon Heterogeneous Ecosystem Energy Balance Studied, enabled by a high-density extensive array of detectors. And if I knew how many times I would have to say that, I would have probably picked a different acronym. Nonetheless, it does a good job capturing what we're going to talk about today. So I'm just going to give kind of the big 10-minute overview of what we're doing and kind of what we did 2 summers ago, which feels almost like a decade ago right now, given the current state of things. And then I'm going to pass it off to Brian, who's been doing a lot of the hard work of really trying to tease out some of the hypotheses from the data that we collected over that time period. So I like to start with just a simple animation, thinking of the world that we live on is populated by biological organisms. And the functions that they do, for example, as shown here in the satellite reflection of photosynthesis, observed through the infrared and green channels, is a significant part of the Earth system. And the way that they change water and carbon cycles and the radiation and reflectivity of Earth influences the physical system in a myriad and complex number of ways, of which many of you are probably familiar with or work on in some form or another. One way that they interface with the Earth system is through the energy balance. And so in this Graham-Stevens image here, what we're looking at is, of course, the global Earth radiation balance estimated by various sources. But the point I want to make here is that the surface of the Earth, which is populated by biological organisms whose functions influence carbon and water cycles, directly influence then the surface energy balance of the Earth, which then feeds into the development of atmospheric properties like the growth and development of the atmospheric boundary layer, the sponge layer that sits between the surface of the Earth and the free troposphere. So I've been thinking a lot about these types of questions for nearly 2 decades. A lot of that happening here up here in northern Wisconsin. So here's a picture of a very tall tower. It's 450 meters or around 1,500 feet tall. It's a television station tower. And both people who came before me, including my PhD advisor, Ken Davis, and his collaborators like Peter Backwin at NOAA and Arlen Andrews, have been working out here trying to understand atmosphere-land interactions. And one of the things I've been wondering about is how can we better understand how this heterogeneity of the Earth system actually influences the atmosphere? And I could have been fancy and gone anywhere on the planet and found something interesting, but we've been studying this spot for 2 decades. And I really thought if we could intensively study this a little bit better, we might be able to understand something. And I like to use this quote from Marcel Proust, right? The true journey of discovery is not in seeing new landscapes, but in developing new eyes. And that's in many ways kind of the goal of this CHEESEHEAD experiment. I do want to acknowledge we've been working out here. This is the Chequamegon National Forest, hence the C in CHEESEHEAD, and also the ancestral homelands of the Ojibwe people whose land was forcibly removed. And so people have been working and looking at this land and understanding it for thousands of years. And I'm just one of many coming into this place, looking at it, hopefully from a new set of eyes. The eyes that we use a lot of are Eddy covariance flux towers, which I assume a lot of you are familiar with. But if not, the basic idea is that we take high frequency measurements of turbulent wind gusts, as well as concentration measurements of water or temperature or CO2 or methane, and use those to directly infer the net exchange between the surface and the atmosphere by looking at the covariance between vertical wind and the scalars. This is a picture of one of the Eddy covariance levels. We have 3 heights on this tall tower where we've been measuring since 1996 fluxes of carbon, water, H2O, methane, and heat and momentum. And we're not the first people to do this. There's a long history in Eddy covariance and going all the way back to early theories of turbulent fluid mechanics in the late 19th century into a lot of pioneering work, including much of that pioneered at NCAR. In making measurements with sonic anemometers and with infrared gas analyzers, as well as then setting up some of the first global networks through Ameriflux and FluxNet, and these data that have been used throughout the world for understanding carbon and water cycles and the Earth's energy balance. This is a big science now. There's this based on this crowdsourced paper from George Burba. There's something like around 2,000 Eddy covariance flux towers that have published data and or are actively operating and submitting data, including the 11 that my lab runs currently. But they all suffer from one interesting problem, which is known as the energy balance closure problem, which Brian will get into more detail. But in these towers, we measured at sensible and latent heat flux, right? The heating and evapotranspiration occurring from the surface by biological organisms and the physical surface. And that's what we measure for our Eddy covariance system. And we also know that those have to be balanced then by the available net radiation and the heating of the soil and the ground and the biomass. And in theory, if the first law of thermodynamics is true, and I'm pretty sure it is, those things all have to balance out. But it turns out that every single Eddy covariance flux tower that's ever been deployed anywhere on the planet fails to show that, right? So here's one of the towers I built in 2001 in the Upper Peninsula of Michigan. I call it my baby, but it's the Sylvania Wilderness, old growth forest. Available energy here on the x-axis is the watts per square meter of incoming net radiation minus soil heat flux and biomass heat storage. And on the y-axis is the sum of the sensible and latent turbulent fluxes. And the one-to-one line in red, as you can see, is above most of the data points. And so here we have about a 75% energy balance closure. And this is actually not that far off from what you see in just about any Eddy covariance tower. As we'll see in Brian's talk, it varies quite a bit by time of year and by type of ecosystem. And that's actually what we're going to be focusing on in this talk. So how did all of that lead to this? This is a CHEESEHEAD, in case you're unfamiliar, which is a foam cheese hat that fans of the Wisconsin Green Bay Packers football team tend to wear. And if you didn't know, that's where that comes from. But the basic idea of this experiment was that energy balance closure is a problem, but it's also an opportunity to investigate potential sources of it and use those to understand how the atmosphere and the land surface behaves. So the CHEESEHEAD experiment really came about several years back, actually about 7 years ago when I was on my last sabbatical leave, working with colleagues in Germany, trying to figure out how could we address this problem. And at the same time, NCAR, through its integrated surface flux systems and its sounding systems, were kind of really ramping up their ability to deploy a large number of flux towers. And so this was supported by an NSF physical dynamic meteorology project, but we also got some funding from the Germans through the DFG, as well as some add-on projects from NOAA. And what we did was we focused on a 10 by 10 square kilometer area around that tall tower, which is call sign is WLEF here in northern Wisconsin in the Chequamegon National Forest, where we have this huge mix of open water, wetlands, and forests, and even some grasslands and urban area. And what we wanted to do was run an experiment from summer through fall of 2019 to be able to evaluate and observe the changes in energy balance as we go from summer where we're mostly a latent heat flux dominated system, to a patchier heterogeneous system in the fall as you have senescence while the wetlands are continuing to be wet. And while we do this, could we observe this in as many places as possible and understand how the atmosphere then behaves in response to it? This involved a large number of partners, including NSF, a variety of partners at different universities, even a few high schools and middle schools involved in outreach projects, and a large crew of close to 70 collaborators across a number of universities in the US and in Europe. And these are just pictures of a few of those who were involved, including several of my own graduate students. And what this group tried to do was intensively sample the air and ground of 35 square miles of northern Wisconsin. And as Jackie mentioned, this is all detailed just in a paper in BAMS that just came out that Brian is the first author on. And so this is a graphic he made of showing you this idea of using flux towers plus airborne measurements plus atmospheric profiling measurements plus surface measurements to really understand and to more intensively measure essentially a single weather or climate model grid box in a way that hasn't been done before. So this started with the flux towers, and what we did was we randomly assigned 100 points from which we worked with Steve Onkley here shown on the right and his crew to identify 19 sites where we could deploy flux towers both from NCAR as well as a couple additional towers from Paul Stoy at Montana State, now at University of Wisconsin. And so here we are at a surveying trip back in 2 years ago. And what we ended up doing, or what they ended up doing, was amazingly setting up a large number of flux towers, both in forested systems, wetland systems. We even put out a lake system or two in semi-randomly chosen spots, partly limited by access and so forth, so that we could actually sample the landscape energy balance and its variation across space. We also then used a field not too far from that WLEF tall tower, as well as the WLEF tower itself, to deploy several profiling instruments, including those from the NCAR integrated sounding system, as well as radio sound launches, some Lidars from the group in Germany as well. We also teamed up with some remote sensing folks in land surface remote sensing, as well as ecologists who set up about 40 or so plots to intensively sample biomass and vegetation, as well as fly some drones and hyperspectral aircraft to sample the surface of the ground to understand what's actually the organisms that are conducting these sensible and latent heat flux transfers. And then we had several aircraft, including University of Wyoming King Air as an LAOF facility, which was flying low-level legs back and forth over this landscape to do flux measurements, as well as a compact Raman LiDAR from Zane Wang's group to do profiles of water vapor and temperature. So this is just a plot of kind of the way all of these transects were done over the course of 3 intensive sampling periods in July, August, and September of 2019. This is the ugly table of all the data we collected. Just wanted to point out we have a website. We've actually pretty close to having virtually all of the data online and available. So please, we've collected more data than we ever know what we'll do with. Please use these data if you have any interesting questions about land atmosphere interactions. There's a variety of other measurements I didn't even talk about that are beyond either end of the domain from NOAA. So lots of interesting things. Happy to chat down later on if you want to get into more details. And then finally, to point out, we did have a number of opportunities for outreach and including an open house we did in the summer with the local community. This is rural Wisconsin, pretty small town. It was a lot of the folks there were really excited to learn both about the research that's been going on for decades that they had no idea about, as well as the opportunity to really interact with scientists from all over the country. And I think especially the teams from Europe and stuff who became locals during that time became good friends with a number of people. So that was my quick and dirty introduction to CHEESEHEAD, and I'm going to turn it over to Brian Butterworth. Brian joined the project about 6 months or so before we started deploying the first flux tower, and he was in charge broadly of a lot of the logistics, the organizational aspects it took to get nearly 40 people into the field, as well as leading a lot of the science questions on energy balance. And Brian has been an amazing postdoc for me in the last 1.5 years. And we're going to continue having him on the project for a little bit more, but he is, of course, looking for his next exciting adventure after this postdoc ends. And so certainly if you have leads or ideas, please keep Brian in mind. He's got both ocean and atmosphere and land surface experience, having done Eddy covariance work on ships prior to this. So keep an eye out for. He's an up and comer. So with that, I'll introduce Dr. Brian Butterworth, and I'm going to have him take over the screen and tell us more about what we're learning.
Okay, thank you, Ankur. I appreciate the introduction. And thank you, Jackie and the EOL team for inviting me here. So I'm gonna pick up where Ankur left off, which is to kind of get into some of our initial results here from the project. And since he did a great job laying it out before me, I'm just gonna mention a few of the objectives that I'm gonna focus on. So we were asking these questions. How does spatial heterogeneity in the land surface impact the Earth's energy balance? And also to look at this hypothesis that mesoscale eddies are an important cause of energy balance non-closure. So that's what I'm going to focus on here. So just to kind of look at the problem that I'll be focused on, Ankur alluded to it, but the problem of energy balance non-closure just refers to the fact that in traditional eddy covariance, it's typical to measure a greater incoming energy than outgoing energy, even though we expect them to balance. And so the energy balance equation on the bottom there is just net radiation minus ground flux should equal our latent heat flux plus our sensible heat flux plus whatever energy is stored in the system. So one possible explanation for this is that landscape variance, possibly in the form of differential surface heating, creates quasi-stationary mesoscale eddies, and that those eddies are not being captured well by a traditional single-site eddy covariance tower. So there's two figures here from different journal articles that just kind of show this as diagrams, and essentially just saying that there may be a bias due to this reason, and that might be the cause, or at least part of the cause. So as Ankur mentioned, we deployed a ton of different instruments during this project, but to get kind of a manageable talk in, I'm just going to focus on a few. So I'm going to focus mainly on the NCAR EOL ISFS tower network. I'm also going to look at Doppler wind lidar data, and I'll also touch on some of our airborne eddy covariance data. And before I kind of get into it, I just kind of want to re-mention here or point out what we mean when we say heterogeneous ecosystem. Although this landscape is relatively flat, you can see from this aerial photograph of the Chequamegon National Forest that, that there's a lot of patchiness, right? So we can see that there's patches of evergreen forest next to patches of deciduous forest. There are wetlands, there are lakes. So that's kind of what we're referring to here. And so with our tower network, the NCAR EOL tower network, there were 17 towers from NCAR, the 2 additional ones from Montana State. Most of them were on these telescoping 33-meter tall towers that are pictured on the left. And at each site, sensible heat flux, latent heat flux, net radiation, and ground flux were measured. And they were installed over a variety of different surface types in the landscape. So just to give an overview then, broadly of what we found with our energy balance from this tower network, this plot shows the energy balance components. It's the mean diurnal cycle averaged over all the towers over the entire 4-month collection period. And so to get oriented with that figure, solar noon is at 1700. And so you can see that with net radiation, we have strong incoming net radiation during the day. And then sensible and latent heat fluxes are in yellow and red. And so they're upward during the day as we expect. And then there are measurable but small ground flux and storage terms. And when we combine all of the components into the energy balance equation, there's a residual. So that is the blue line there. And so that's our non-closure term. And if we look just at that, we find that at night we have this weakly negative residual, and during the day we have a strongly positive residual. And so on any given 24-hour period, we usually have a net positive residual. So we found that energy balance varies over the course of a day, but we also see that it varies over longer timescales as well. So this is a plot showing the daily mean energy balance residual for all the sites over the course of the season. And so the individual points here represent the different sites, and then the line through it all represents the average. And so you can see that during the height of the summer, we have energy balance residuals of about 50 or 60 watts per meter squared. And then as we move on into the fall, those decrease. So there's this seasonal trend. The other thing that this plot shows us is that across our domain on any given day, we have a lot of variation in the residual. So it can be on the order of 100 watts per meter square range, depending on the site that we're looking at. So another way to look at this variation in time and space is to look at a map of the energy balance as it changes each day. So this is going to be a little video here that shows the daily mean energy balance. Here it's going to be depicted as a ratio of the sensible and latent heat flux over net radiation minus ground flux. So that can be interpreted as a 1 here represents complete closure, and as it gets more and more yellow, that represents poorer closure. And so as we proceed through the season, you can see that there are these pockets of good and bad closure depending on where we are. And we find that they don't stay put. So it's not that there's one area that's performing really poorly and others that are just always doing really well. It moves around. So this map is just a very simple interpolation from the 19 sites over the tower. So it's not necessarily a defensible energy balance for our grid cell, but it's just to give an example. And so we asked this question then, are these patterns due to mesoscale eddies? So if there are these eddies planted over our domain that are larger than any one tower can see, how can we account for them? And so one way we're going to look into doing that is we're using the Doppler wind lidar data set to identify mesoscale eddies. So as part of the project, we deployed 3 halo photonics wind lidars. They were located right next to the LEF tower. One was oriented in a vertical stare mode, and there were 2 that were placed 90 meters away that were doing range height indicator scans. And so the 3 of them together constitute a virtual tower for measuring 3-dimensional winds. And this work was done by Louise Fahner. She calculated the data set and installed these. She's at Karlsruhe Institute of Technology. And so just to show what this data set looks like, the top 2 plots here represent the horizontal wind and the vertical wind speed on a random day. So this is August 21st. And you can see that we have data from about 200 meters above the ground to about 1 kilometer. That varies, but that's about the average height that they measured. And we have 1-minute averages, so that's the temporal resolution. And so the goal was to use this data to identify the existence and the strength of mesoscale eddies. And the key piece to look at here is the middle subplot, which is vertical wind speed. So what you can see is that at the start of the day, and all the way up until the sun rises, there's very little vertical wind speed. So we have these stable nocturnal boundary layer with laminar flow. But then when the sun rises around 12 or 1300, you can see that the vertical wind speed increases in magnitude, but it oscillates between positive and negative. So we go from about -2 to +2 meters per second here. And particularly at the height of the day, we find that we have really long oscillations that can last up to an hour or more. And so we interpret this as an indication of mesoscale eddies, just based on the time scale and the strength. And so our goal is to be able to tie what we see here in the LiDAR data to the energy balance components that you can see pictured on the bottom for the entire collection period. And so the variable that I'm going to use to isolate mesoscale eddies is the angle of attack, which combines the horizontal wind speed with the vertical wind speed. It's pictured here as a column average of the LiDAR data. And so what we see here is that we have very similar oscillations as we have in the vertical wind speed. And so during the daytime period, so the yellow boxes represent the daytime periods. And so during the day, we have these oscillations that can range from -10 to +10 degrees. And then at night, same thing, we have laminar flow, so there's not much in the way of angle of attack. So then to come up with a way to quantify this, we zoom into just the daytime periods where we have these oscillations, and we get a measurement of the mean period of these oscillations on it every day. So on this day, August 23rd, it was 44 minutes. And we also measured the mean amplitude on this day, 4.2 degrees. And we're going to use those to create an index for the strength of mesoscale eddies. And the way these break down over the course of our data set, these are the histogram for the mean period and the mean amplitude. And you can see from the period histogram that we, on average, have a mean period of about 37 minutes. And the day with the longest mean period, it was 55 minutes. And then with the amplitude, on average, we have amplitudes of ±3 degrees. And the day with the largest value, it was ±6.3. So we use that data set to create this mesoscale eddy index, where we use the mean period and the mean amplitude from each day. And for each of them, we divide it by the mean period and the mean amplitude, the largest mean period and the largest mean amplitude from any day during the study period. And those are equally weighted, which is why it's 0.5 times one plus 0.5 times the other. And so what this will give us is a mesoscale eddy index. For each day, we'll get a value that ranges from 0 to 1. That gives an indication of the strength of the eddies. And where a 1 represents really long period, really strong amplitude or large amplitude oscillations. And so that represents strong mesoscale eddies. And then as this mesoscale eddy index goes to 0, that represents weak or non-existent eddies, mesoscale eddies. And so because those values in the denominator, they were 55 minutes and 6.3 respectively, this is what this equation looks like for our data set. And so we can use that and plot it against the energy balance residuals from the tower network. So the y-axis here is energy balance residuals. It represents the daytime energy balance residual averaged over all of the tower network, the entire tower network, for just that same daytime period that the mesoscale eddy index was created. So 9 to 3 p.m. local time. And so what we see is we have this really strong relationship here between the mesoscale eddy index and energy balance residual. But there's one other piece of information is net radiation is represented by the color of the dots. So you can see that net radiation also is strongly related to the energy balance residual. And this is an expected find. We would expect that on days, say a cloudy day where net radiation is really low, that because there's not a lot of energy coming into the system, there shouldn't be a really large residual. So there are two things that appear to be playing a role here, but I guess the question then is, do mesoscale eddies actually play a role, or is this just a result of net radiation? So one way to look at that is we've removed, if I remove the regression line for the entire data set, and I just run a regression through binned periods with similar net radiations, we see that there's still a relationship for each one of these different bins. And these new regression lines aren't as steep as the original. So that suggests that probably the original line was a combination of both net radiation and mesoscale eddies and maybe other factors as well. But this gives us some confidence that mesoscale eddies may still be playing a role in increasing the energy balance residual. And so just to get a kind of kind of a quick and dirty number on how much they're increasing energy balance residual, we can look at how large of an increase in energy balance residual magnitude we see for each one of these sets over the range of mesoscale Eddy indices, indices that it ranges over. And so in each case, with each different set of bins, we see that we have an increase of about 40 to 50 watts per meter squared. And so, I mean, that's a significant amount of energy, but I think it's important to point out here that that does not account for all the energy that is not accounted for, right? There's still for any given one of these bins, if we remove the influence of mesoscale eddies, there's still going to be a residual. And so that kind of brings us into the next bit here. I just briefly wanted to touch on some other areas that we're looking into. So there are other things that are known to affect energy balance. And so with this data set, we have a really good opportunity to look into those as well. So things like the vegetation type, canopy complexity, and biomass storage are all components that may be influencing energy balance. And so because we have measured over a variety of different vegetation types, we can measure the energy balance components separately and kind of look at how different vegetation types are influencing closure. And so here is a plot. The left two plots show sensible and latent heat fluxes, and these are diurnal averages for the different surface types. And what you can see here is the exact magnitudes of these doesn't necessarily matter for the talk, but we can see that there are differences. So there are very clear differences. For example, say latent heat flux, both evergreen and deciduous forests show the strongest daytime heat flux there, more so than wetlands and lakes. So there are ways these are going to break down, and this data set's giving us an opportunity to look at it. So we've run the numbers just roughly on these different vegetation types. And so the plot on the right here shows the energy balance ratio again. So the heat fluxes over net radiation minus ground flux. And we found here that the forested sites have the best closure, better than the wetlands and lake sites. So this is just something that's going to get looked into a lot further. And this is going to be particularly interesting once the hyperspectral imagery comes in, and we can get even finer grain detail on these vegetation types. The other thing we've looked at is canopy complexity. So the US Forest Service had a leaf-off LiDAR data set collected over the entire domain in 2018. And we used that to get a tree height estimate where we took a digital surface model, we subtracted a digital elevation model, and we have estimated tree height at 1 meter square resolution. And we use that to get a canopy complexity estimate as a standard deviation of the vegetation height in meters within our flux footprints. So that's what's plotted on the x-axis in this plot, and it's plotted against that energy balance ratio on the y-axis. And so what we found is that lower complexity sites show better closure. And so this result is similar to previous findings, Stoy et al. 2013. But it's good that, it's good that we have the ability to look into this because this is going to play a role. And so it's something else we're going to need to account for. And then the last thing I wanted to touch on, something that's often overlooked in energy balance studies, just because it's difficult to measure, is biomass storage. And we were lucky to get an estimate of that here. There was a group from the Chequamegon High School that deployed some tree temperature instruments towards the end of the field campaign, but it overlapped. And we used those to get an estimate of biomass storage. So this data was done by a high school student, Danielle LaLuzerne, who worked with Ankur over the summer. And she used the tree height estimate as just described in the previous slide to get an estimate of diameter of the trees at breast height. And then that diameter value, that was an estimate using allometric equations that are published in the literature. Then she used that diameter value combined with published density values to estimate biomass at the different sites. And then using the biomass plus the tree temperature data, we were able to estimate a biomass storage value. And so the plot on the right shows that. The blue line is the energy balance residual averaged over the entire domain. And this is just a random week, just to kind of show what this data looks like. Biomass storage here is in orange, and there are 5 different sites. And so what we see here is that there are some sites where there's very little biomass storage, but we have other sites that have a really clear diurnal cycle and magnitudes that are not negligible. So during the daytime, some of these sites have been going up to 20 or 30 watts per meter squared. So they definitely don't account for the entire energy balance residual, but they do account possibly for a measurable chunk of it. So that's where things stand kind of with the tower network data. But I also wanted to tackle this question of mesoscale eddies from a different angle. As Ankur mentioned, we had this eddy covariance from aircraft data set, and it's a pretty unique data set. It's a very large airborne eddy covariance data set. We had 480 flight legs. They were 30-kilometer long flight legs, and that ended up being 72 flight hours over 12 different days. And transects were flown at 100 meters and 400 meters above ground level. And so the plot on the left, the map, shows all of the flight legs that were flown during the project. And we can calculate fluxes here using wavelet decomposition. So the plot on the top shows a wavelet cross-scaleogram for latent heat flux. The y-axis shows the scale of eddies, and the x-axis shows the distance across the flight leg, and the color represents the direction and the strength of the fluxes. And so traditionally, to get a latent heat flux, you would integrate over all the scales of motion, and you would get latent heat flux as plotted on the bottom plot. So latent heat flux over the flight leg. And you can see that there's a lot of variation in the latent heat flux over the space. That's a really interesting result in its own right. But for today, I'm actually going to move on to a different aspect of this, which is separating different scales of motion into separate flux contributions. So the other thing that wavelet decomposition allows us to do is it allows us to isolate specifically for scales of motion we're interested in. So here we've isolated what we're calling turbulent fluxes from mesoscale fluxes using a cutoff of 2 kilometers. So any eddy that was smaller than 2 kilometers, we integrate over those scales of motion and we get turbulent fluxes. For any eddy that was larger than 2 kilometers and less than 20 kilometers, we can integrate over the cross-scaleogram and get mesoscale fluxes. And so, so what that allows us to do is plot these 2 contributions, these 2 scales of motions, the contributions from these 2 separate scales of motion separately. So this plot here shows the sensible heat fluxes from all the 100-meter legs. And these are leg averaged sensible heat fluxes. And this is just from one day, from one leg, or just from one day, August 23rd. And you can see over the course of the day, there was a morning flight and there was an afternoon flight. And so what we can see is if we look just at the blue bars, those are the turbulent fluxes. And you can see that those dominate and they go up to about 100 watts per meter squared during the day. But if we look at the orange bars, we can see that there is a significant contribution from mesoscale eddies, where during the afternoon, we're seeing sensible heat fluxes from the aircraft data set from this mesoscale range of 50 or 60 watts per meter squared. And so I guess I should just also mention here, on this day, August 23rd, the mesoscale eddy index was large. And so So it was the Lidars showed that we had strong mesoscale eddies, and then we're seeing large contribution here from the Airborne eddy covariance data set in the mesoscale range. But we can plot this same thing on a different flight day that didn't have as strong a mesoscale eddy index. So here again, sensible heat flux on the y-axis. The blue bars represent the turbulent fluxes over all the flight legs of that day. And you can see that they dominate like before, but here we see that the mesoscale eddies, the mesoscale flux contribution is a lot lower. And so during the afternoon, it peaks at about 10 to 20 watts per meter squared. So that was just sensible heat flux. I wanted to show here what this looks like when we add both the sensible heat flux and latent heat flux together. So, you know, the main components of 1/2 of the energy balance equation. So these stacked bars represent sensible and latent heat flux, sensible heat flux in yellow, latent heat flux in orange. And so on the left plot is these fluxes from August 23rd. And you can see that during the daytime, we have an average of about 90 or so watts per meter squared. Whereas on September 26th, we have much lower mean heat fluxes at about 40 or so watts per meter squared. So again, we're seeing its difference of about 50 watts per meter squared between days with a strong mesoscale eddy index and days with a weaker or lower mesoscale eddy index. So using these two data sets, we can come up with some just kind of like initial kind of conclusions. We found that mesoscale fluxes are not negligible. That's very clear in the Airborne eddy covariance data set. We can see that flux contributions on a summer day can exceed 100 watts per meter squared. And that not all of that energy is being captured by traditional eddy covariance measurements. So the tower-based EC results, they showed that mesoscale eddies are increasing our energy balance residual by about 50 watts per meter squared. So the towers may be capturing some portion of mesoscale eddy contribution, but quite possibly not all of it. And so the question then is, how can we account for these mesoscale eddies? So one obvious solution would be to increase our averaging interval. So if we measured fluxes over 3 hours or 6 hours, we would likely close, at least to some degree, the energy balance problem. And literature has shown that this is the case, that you have smaller closures, that you have a smaller non-closure. So there's a smaller residual using a longer averaging period. But there are several issues there. The first being using a longer averaging period sometimes will also include not just the things you want, but also things that you don't. So the influence of advection, let's say. But even if that wasn't the case, there's another issue, which is there are a lot of the science questions that we're interested in that require a higher temporal resolution. So a 6-hour flux interval may be useless for certain types of science questions. So we'd like to know, is there a way to account for these mesoscale eddies while also maintaining a high temporal resolution? And so we're looking at this problem then of, can spatial eddy covariance improve energy balance closure? And so spatial eddy covariance is a little different from a traditional eddy covariance setup. In traditional eddy covariance, you would have one tower and you have to infer spatial information of your eddies using Taylor's frozen turbulence hypothesis. Whereas with spatial eddy covariance, by deploying many towers over a region, you can sample those eddies simultaneously across the many sites. And so this has been done in the past, but it's typically been done at very small scales. So like the one pictured here. And we're gonna run this for CHEESEHEAD, which is at slightly larger scales. So we have a 10 by 10 kilometer domain. And the reason we've gone down this avenue is Ankur's previous grad student, who's now a postdoc at University of Michigan, Ka Zhu, she just recently published a large eddy simulation study that tested spatial eddy covariance, and it found that 89% of the prescribed energy fluxes were captured using spatial eddy covariance, which represents a bit of an increase in a little bit better closure than normal. But then using a spatio-temporal method, that the LES captured 95% of the prescribed energy fluxes. So even better energy balance closure. So our goal was to test these findings using the field data. And just to kind of give some background here, just to describe spatial eddy covariance, I should first describe traditional temporal eddy covariance. For both, the flux is calculated as the mean air density times the mean covariance in fluctuations between vertical wind speed and a flux quantity like temperature or water vapor. And the difference between temporal eddy covariance and spatial eddy covariance is going to come down to the fluctuation components. So, for a standard temporal eddy covariance, we will get our fluctuation component as the instantaneous value minus the time mean. So the 20 hertz value minus the 30-minute average. So for vertical wind speed at the bottom, you would have the fluctuation component is the 20 hertz vertical wind speed minus the 30-minute average vertical wind speed. For spatial eddy covariance, we calculate that fluctuation component as the instantaneous value minus the spatial mean, so the mean across many sites. And then for the spatio-temporal method, that's a combination of the two. So you would subtract, to get the fluctuation component, you subtract instantaneous value. You take your instantaneous value and you subtract the space-time mean. So that would be the mean across all sites. So here, 19 sites averaged over all the sites over 30 minutes. So the question then is, how do these different eddy covariance methods impact energy fluxes? So these two plots show the daytime latent and sensible heat fluxes averaged over the entire study period. And they're broken down into the different types. So temporal, spatial, and spatio-temporal. And what we found is that the spatial eddy covariance method increased both sensible and latent heat fluxes slightly, and that the spatio-temporal method increased them even more. And so when we combine the influence of both sensible and latent heat flux with the spatio-temporal method, we see an increase of 40 watts per meter squared over the traditional temporal eddy covariance method. So larger fluxes by a meaningful amount. And so how does this influence the energy balance closure? So for spatial eddy covariance, we saw a daytime energy balance residual. We saw it reduced by 7%. And using the spatio-temporal eddy covariance method, we saw daytime energy balance residual was reduced by 25%. So then kind of going back here to the previous plot, this is the same plot I showed earlier, but using the spatio-temporal method. So this is energy balance residual on the y-axis, the mesoscale eddy index on the x-axis, and the points here are calculated using spatio-temporal EC as opposed to the traditional eddy covariance method from before. I'm going to cycle back and forth between the two just so that you can see the difference here. So that was the original plot. And then spatio-temporal, we see that it goes down. So traditional, spatio-temporal. And so what we find here is that there's a reduction in the residuals using the spatio-temporal EC, which we expected based on the previous plots. But what's interesting is that we see the greatest reductions for days with strong mesoscale eddies. And that at the lower, and the days with weaker mesoscale eddies, we don't necessarily even see a reduction in energy balance residual. We really just see an increase in the variability of the residual. So I'll show this again. The traditional, so you can see if you focus just on the days with large net radiation and large mesoscale eddy indexes on the right side of the plot, and then they drop pretty consistently, but then we see the increased variability at the low end. So, so what we found here from this data set so far is that energy balance is varying in time and space. It varies both diurnally and seasonally. We've shown that we can identify mesoscale eddies using Doppler wind Lidars, and also using a wavelet decomposition of our Airborne eddy covariance data set. The Airborne eddy covariance showed that contribution from mesoscale eddies may exceed 100 watts per meter squared on summer days. And using the tower network, we showed that the mesoscale eddies are increasing the energy balance residual. And that increase might be on the order of about 50 watts per meter squared. So where we're going with this, kind of an immediate thing to do next is to investigate the flux co-spectra to see if we can isolate the scales of motion that are actually contributing to our fluxes. That's kind of just to get into the nitty gritty. But more broadly, a lot of things I showed today were averaged over the entire domain. But we have this data broken out into, there are 19 different towers. So there's lots of work that can be done and is going to be done moving forward, looking at the spatial patterns in the fluxes and seeing if they have any relationships with different surface characteristics. So that is going to include canopy traits, specifically the hyperspectral imagery, which is being processed right now. And also we're going to look at it in terms of land surface temperature. So Ankur didn't mention it, but he's working on a downscaling algorithm to get a higher resolution land surface temperature using eco-stress data. So we're going to be applying those new data sets to the Flux Tower network data as well. And lastly, we're going to be applying a machine learning algorithm, the environmental response function, which was developed by Stefan Metzger at NEON. That's going to break down the things that are contributing to the fluxes at even higher resolution and give us kind of a greater insight. So Ankur mentioned it, but if you are interested in learning more about the CHEESEHEAD project, there's a paper coming out in the January issue is the one it's slated to come out in, but it's already online on the BAM's website, so you can find it there. All the data is on the NCAR EOL repository. We'd like to thank Linda Cully for doing an amazing job wrangling everybody and getting things online. And then lastly, we have some additional information about the project and about site characteristics at cheesehead19.org. So thank you for tuning in. I really appreciate the opportunity. I'd be happy to answer some questions, but if you don't get a chance to ask one now, please feel free to email me. So my email is at the top. All right, thank you.
Thank you, Brian. Thank you, Ankur, for a really great presentation on CHEESEHEAD, the CHEESEHEAD project. Really appreciate the cool animations. I would like to make time for questions. Again, please use Sligo, which is at the bottom of the presentation screen. And we have a question from Dave Turner. The contribution to the latent heat flux by some of the mesoscale eddies varies by a factor of 3 between some adjacent flight legs. Is that just sampling error? What is the sampling and random uncertainties in these heat flux values from the King Air?
So I don't have a solid number on that right now, but I guess just broadly looking at it, if you recall the plot of latent heat flux that was on the bottom of that slide, there was really large variation even across any given flight leg. So I guess I really don't have an answer for you in terms of actual number, but I wouldn't be surprised if those are real. So what we do notice is that as we go over different land surface types, like as we cross over a lake or a different type of forest, we see these completely different jumps in our latent heat fluxes. So I don't know. It could be partially both.
Yeah, and I would agree. Just from I'm relatively confident on that the random uncertainty, even using this wavelet approach, which kind of splits up the flux into a smaller segment, is relatively modest, maybe like 10%. So the change in the mesoscale contributions, at least based on this simple method that Srinath Pillari has been working on for his PhD, should be relatively robust. But it is interesting, right, that you see these really large jumps from one leg to the next, even though they're less than a kilometer apart and less than 20 minutes in time. To be determined what's actually driving those.
Great. I think we have another question. We have a question from Frank Colby. Presumably, the stronger mesoscale eddies have longer lifetimes. Is there any evidence of seeing them propagate through the network?
So as of right now, that hasn't been looked into, but it's a good thing for us to dig into next. Since most of what I showed today was just averaged, we were looking at averages across the entire domain. Yeah, it wasn't a good chance to figure that out, but yeah, that's something we'll look into, and it should be able to be something that we can look into. So,
and it's something where in addition to the Doppler Lidars, the integrated sounding system really provides a nice kind of way to look at propagation, both in the solar arrays as well as looking at the upwind and downwind information taken from the microwave profiler set up by NOAA. And so I'm really excited about seeing that, just seeing something propagate through the network. I'm confident that we'll be able to detect that.
Great. I think we have another. We have a comment and a suggestion from Dave Turner. Don Lenschow has developed methods to estimate both the sampling and random uncertainties in these fluxes. I would encourage you to consider using his approaches. I see some head nodding there.
Yep. We're familiar with those approaches and the classic papers on those. The challenge with the wavelet fluxes is there are some assumptions that are different, and so I know that Srinath has been working on this, and so we're just kind of waiting to see where that comes from that. But yes, that's a good point. It's essentially right. The shorter your leg averages, the smaller your distances, the greater your uncertainty is going to be.
As we wait for potentially more questions to come in, I have a question. So you showed an example of an energy residual plot over the course of a day. This was in the beginning of, I think, Brian, your talk, and it looked like in the sunrise and the sunset that the energy residuals were a minima, meaning like it tended to zero. So it seemed like sunlight, or at the start of sunlight, the initiation of sunlight or the disappearance of sunlight was an important component. Like not being a boundary layer meteorologist, can you comment on the dynamics of what happens during that time and the consistency and robustness of these residual minima during sunset and sunrise and sunset?
Well, so my guess is the reason that goes to zero there has more to do with just the transition between negative and positive. And not that sunrise and sunset happen to be particularly good for energy balance closure, though I guess, yeah. I mean, that's where I think it is. So at night, because we've transitioned from different directions of the fluxes to the daytime, as the sun hits the surface, we have surface heating, the boundary layer rises. So we're just seeing this transition in the atmospheric environment at that moment that's causing just a switch, but not necessarily that's a particularly good time based on the amount of sunlight is I guess how I interpret the question.
Great, thanks. I think we have another question coming in. We have a question from Lauren White. It seemed that the period of the eddies increased later in the day. Is this most likely related to the deepening of the PBL being paired with larger scales?
Yeah, I think that's exactly right. I think, yeah, as the, I believe that's what's happening, is that as the day goes on, you know, we have this convection, it starts to develop. So you get larger and larger eddies as the boundary layer is developing, that you just couldn't get when the boundary layer is smaller, you know, just after sunrise.
Yeah, and it actually hints at kind of how you might go about creating a generalized correction to energy balance. So one of our colleagues, Matthias Mauder, has been doing some LES-based studies where with virtual towers in the LES showing that you can use scaling variables like boundary layer depth and W star and use those in a way to come up with a systematic way to reduce the energy balance residual at a single tower. And certainly something like boundary layer depth, which is you could measure even with, you know, a ceilometer. And in our case, we have multiple measurements of beyond ceilometers, including an aerosol lidar and others, would be a good one to test on the network.
Great. I think we have a final question. We have one final question from John Gilly. What led you to choose 2 kilometers as the scale to separate turbulence from mesoscale eddies?
I am basing on the papers. So this work was done by Srinath Pillari, who's Ankur's graduate student. And there are 2 papers. I think Matthias Mauder has published one of them, and that's just what they had chosen. So that's just where we started.
Yeah, it's somewhat arbitrary for sure. And really what we're thinking of is, you know, if you think of traditional scale diagrams of the atmosphere, there tends to be a energy minima between the turbulent resolving scales that kind of come up to around 1 kilometer, 15 minutes-ish or so. And then you have the more mesoscale to synoptic scale contributions. And so in some ways, you know, Srinath will be testing this a little bit, but in theory, it should be relatively insensitive in that range of plus or minus a few around there until you get into the scales at which you would expect larger scale invective type scenario occurring.
Great. So we are just past the hour of our seminar. If you're particularly interested in this research, please reach out to Brian or Ankur via their email, which is provided in the seminar flyer and also in the presentation. On behalf of EOL, I would like to thank Doctors Desai and Butterworth for giving us the opportunity to hear of their flux-based research in the Chequamegon National Forest. Thank you, everyone, and have a great day.
Cool. Thanks for having us.
Yeah, thank you, Jackie.
Take care.